Right, hello everyone. I'm Wes. I work for Server Density. This talk will all be about HTTP and also service-oriented architecture, asynchronous requests, that sort of thing. This is who I am. I'm at first VAMP in most places. That's the #1. There's a long and boring story behind that you can always ask me about later. So yeah, I release lots of open source code on GitHub, but you can check my page. And I also curate PHP Weekly for my sins. So we should all be aware of what HTTP is. It's the protocol that powers the web. It's been around for quite some time, for over 20 years now. And it's changed very little in that time. As I say here, it was expanded in '95 with 1.1 and some actual specifications being released. And it has remained pretty much a very, very simple protocol. It's pure text with a simple carriage return and new line separator between those text blocks. It has a very descriptive metadata portion to its transfer. That's the headers part. Actions are resource-centric, so you get a resource, you post to a resource, you put a resource, you delete a resource, etc., etc. The body can contain any data, usually text, but you can wrap any binary data in there that you like. That's how uploads and downloads usually work. They get wrapped in a MIME wrapper. So as I said, very little has changed, but a few things are beginning to change over the last few years. We're currently getting extensions to HTTP like server-sent events, which exist purely by adding extra headers and an extra portion to the request itself. And WebSockets, which, while using HTTP to initiate the initial connection, actually are an almost entirely different protocol. And we get new protocols along the way. Speedy, which some of you may know from Google Chrome, but it also has support in Firefox and a few other browsers now, is effectively HTTP version 2, or what Google want to be HTTP version 2. There is now a standard proposal for HTTP 2, which is based on Speedy. And that just streamlines how HTTP works. It means you can send multiple requests with the original request without having to build this massive connection up first, as well as making compression part of the whole stack rather than an add-on. So at Server Density, we've spent the last year re-architecturing our services with a service-oriented architecture. So everything is its own HTTP service. It sits alone from everything else. So we have a user service, an inventory service, a cloud service. And one of the pure joys of HTTP is the fact that everything speaks HTTP. Everything. So you have a cluster of workers over here and a cluster of workers over here. They can all be sat in front or behind of a load balancer. And that load balancer can be, it could even be Apache if you want. We use Nginx because Nginx works both quite well as a web server and as a load balancer and proxy. But that can be pretty much anything that knows about HTTP and can route HTTP requests. And that means that you can do all the standard tricks that you would with your web stack with your services, with your backend services. They work exactly the same. You can do things with headers, you can add compression, you can add extra data along the way. Our services are all RESTful, so we get that advantage. RESTful, if you don't know, but most people should, is basically just a way of looking at things as resources and using the HTTP request the way they're supposed to be. So a GET request will retrieve an item, a POST will create a new item, a PUT will update an item, etc. They're stateless because they don't need to know about sessions or authentication or anything like that. And in fact, doing that, as I'll discuss later, adds a lot of extra complexity to your stack. It's mostly a series of thin layers, so we do a lot of MongoDB work, and most of our services are effectively just a thin layer on top of MongoDB. You push a JSON object into the service, and it gets stored as a BSON object in MongoDB with a bit of validation in the way to make sure you're not pushing arbitrary data in there. We have a common documented API because it's all HTTP. If you can speak HTTP, you know how to speak to a particular service. Actually, documenting that service is really easy because you're just documenting the regular gets, puts, etc., and everything has IDs. And as I say there, everything is callable from the front end, which works quite well with the current trend of JavaScript-heavy front-end applications. So all of our requests from the front end are literally calling the same API that our back-end servers talk to each other. As I say here, everything can do HTTP, and almost everything does HTTP asynchronously. As I said before, the UI, the front end, is almost pure JavaScript, which means everything needs to be non-blocking because you don't want to block the user interface. And you also get the added advantage of having, air quotes, real-time, the ability to push updates down to the front end and have them appear on the screen. So things like Socket.io and Sock.js make this really easy because they wrap WebSockets and server-sent events and give you a common JavaScript API on the front end. Now, what do I mean by asynchronous? That bit confuses a lot of people. They often confuse asynchronous with concurrent. Concurrency and asynchronicity are two related but different things. By asynchronous, I mostly, from services point of view, mean non-blocking. So if I'm reading a file, if I'm reading a request from the browser, if I'm pushing a request back out to the browser, if I'm talking to the database, I don't want to block my process. I want to be able to do other things at the same time. But that's where you get workers as well. As I said before, clustering. You can cluster workers, so instances of web workers, of task workers that push things out to queue, they can all be clustered, and you don't want those things to block. You want to be able to keep pulling work in, processing them, and pushing work out as soon as your CPU is done. You will need to unblock your CPU and leave the operating system to push everything out to a network stack or whatever. And it also has consequences on the front end, because the front end is asynchronous as well, in the same respect that AJAX requests are all asynchronous. You push an AJAX request and you work with another event in the browser. You also have new APIs like web workers to contend with on the front end as well, which allows you to do effectively multiple processes. But that's for another talk. So let's take a little step down a user clicking a button. Click. So a user clicks a button, it issues a JavaScript event. You've got a bit of code to handle that event being fired, and then that issues an AJAX request. You get a nice little stream of ones and zeros after the browser's put it all together with some text. That goes off somewhere to a mystical server in the cloud that handles that request. This could be a router, it could be the application web server itself. From our point of view, it's going to be an Nginx load balancer which unwraps these headers. As you can see here, you have a GET request with some cookies and a content type, and it may accept various things. So these are an example of applications which can handle a HTTP request and do something with it and route it somewhere else. Even good old Apache, the feather sitting there, can route requests for you. I wouldn't do it with Apache, but it can do. The advantage here is that you can do things like unwrapping SSL, unwrapping compression. So SSL termination is a great trick. The idea is you get an SSL request coming into your front-end load balancer. Your front-end load balancer unwraps the HTTP request outside of the SSL, figures out where it needs to route that based on the host name or the path in the URL, and just sends that back off as a normal HTTP request. That way your backend services don't need to give a crap about SSL. They just receive a normal HTTP request. You don't need to distribute certificates to every server under the sun in your backend, especially if you've got a 10,000 node cluster out there. They just get a normal HTTP request coming in. The same with compression. They can get ungzipped or gunzipped and just a normal HTTP stream coming back through. It can also do other things like adding on extra headers to the request or things onto the query string. So your application code here, it receives the request, it does something with it, it sends back a response. The response is almost identical to the request that came in. You have some headers, we define a content type, JSON of course, content length. I'll talk about the X barium header that I've added on here. That X is a convention in headers of basically saying it's a custom header. They're beginning to drop this convention in a lot of applications because it's seen as muddying up the waters. It's still used all over the place because it helps prevent you overrunning with a vendor's header, something that will actually be used by browsers. I'm using the connection closed header here, which is a special header which says once you have filled that content length, so as soon as I've read 14 characters from the response, close the connection. I don't care any longer, just close it. Which is often used for tricks like performing extra tasks after the connection, but can also be handy for saying content length 0 connection closed from the client. As soon as I've got a response, I don't care about you any longer, I'm going to go do something else. So, as I said before, authentication, session handling, SSL termination, all those sorts of things are the sort of things you don't want to have in your backend services because that means pushing out extra libraries, certificates, all sorts of things to all of your code bases. And here are some other common problems with talking from the front end. Multiple backend servers, your JavaScript front end. The biggest problem here is that you're talking to multiple backend services. So I've got a users.mydomain over here, an inventory.mydomain over here, and talking from the front end, you've got cross-domain issues. And you also probably don't want to make your backend services externally available. You don't want to say, I want to query all the users on your system by just talking to your backend users service, because that would be madness. That would just open up everything. That would be a massive security hole. And, well, for various other things, you could have DDoSes, anything. So one way we got around this was by building a system called Socky. And Socky, from the first point, was to allow us to have WebSockets interface with our backend services. So Socky does WebSockets using socket.io, but it also handles adding our session data on. So it can talk to the session store, and it knows about the cookies from the front end. And it then just adds on extra user IDs and account IDs when it unwraps the request that comes in and forwards those requests back onto the backend services. So the backend services just get a user ID in the query string and an account ID in the query string, and they can just use those for their MongoDB queries. By doing that, none of them care about sessions. None of them care the fact that you've been through a login process and gotten yourself a session. We just say when you hit Socky, if you don't have a session, you're not going to get to any backend services because they're only routable by Socky or an internal service. And the routing itself goes through one single point. So you hit less cross-domain issues because we just map a single host and URL path for Socky. So you hit /svc on the site and you're hitting Socky, and that hits a backend service by routing /svc/users to a users.mydomain in the backend. I mentioned the X barium header before. This is a little trick we've introduced for debugging. So every request that comes in through, for example, our alerting system will have an X barium header added onto it by our routers. And this is just a unique enough ID. So it's a UUID4, which is generated from the host, etc., and a bit of entropy. And this just gets added on as an Exparium header and hits our alerting system. The alerting system loads up the payload into a database, adds on the Exparium header to a field in the database, and then our alerting cluster, which processes all these payloads, an offline process, will also unpack this Barium header, add it onto the next part of the process, and the next part of the process. And eventually it will hit another service, a notification service, if there was an alert sent. So, for example, you've got a disk usage alert. You're using too many. You've got a 50% disk usage alert on a mount point on a box somewhere, and you want to receive an email because that's a bad thing. Our notification service will receive a request from the alerting system and say, send this email to user X, and it will also have the Barium header attached to it, which will then also be attached to the email as an email header, which means when the customer receives this email, they can just forward that email back to us if there was a problem with the alert. Say their box is only 40% full, and they got an alert saying it was 50% full, and it woke their ops up in the middle of the night, and they're really pissed about it. So they can just forward this email on to us. We'll look at the email and says, there's a Barium header there. We'll just copy that, and we'll query the notification service, or we'll query the alert system, and both will have the same ID because it passed all the way through. Or we can go to our log aggregator, which collects all our logging. Because we logged the Barium header whenever we did a logging call, we can just query for that Barium ID, and all of the log entries which matched that particular pass through our system will come up. It's an incredibly powerful thing to do. It's a simple thing to do, add a unique ID to everything. But because HTTP has a rich metadata system of simple key value headers, you can add it to everything, and everything can understand this and unwrap it and add it to something else. So another problem we had with how our system works is that we have these clusters of task processors doing things like, for example, polling cloud providers like Amazon or Rackspace for updates, so that we can tell you what your latest deployed servers are on our dashboard. Because you may have deployed this for Amazon. You may not have clicked on the button on our dashboard and deployed the server. You may have deployed it for Amazon, or you may have deployed it for Rackspace. But unfortunately, the only way to get updates about either of those is to pull their services for those updates. So we have a task running in a cluster which continuously pulls for those updates and syncs it back with our data. But how do we get that back to the client when the client has a single long-running WebSocket connection to one of our back-end instances? That back-end instance doesn't know about the cluster, about the workers in that cluster. So we came up with the concept of a registry of web hooks. So people may know web hooks from GitHub. When you add different services to GitHub, you can add an extra set of web hooks for the services, and once an action happens on GitHub, that action will be sent back as a HTTP request to one of those services, and that service will have that data. And it's all nice and push and asynchronous. You don't pull for the data, you get it when it happens. So we wanted a many-to-many pub sub system, publisher subscribe, where you could have multiple users logged into an account. And you only have one sync task for that account on the back end. And all of those users need to get the updates for that sync task back. So when you're logged in, your account and user for that WebSocket handler is subscribed to events for that account. And when the task runs, it literally, here's a bit of Python. It literally looks up a webhook collection in MongoDB, loops through them all, and sends a request, sends a post off to that host. So those will be unique host names in the URLs, actual back-end host names, as opposed to load balancer host names. Because if you hit a load balancer, you don't know where it's going to end up at the end. It's getting balanced. So these are, for example, cloud service host names on particular ports that will receive this post request, with an account ID and user ID and say, I've got users connected over a WebSocket, interested in updates for this account ID. I'll send this information back over the WebSocket. And the JavaScript in the browser will handle these events coming over the WebSocket and display updates to their cloud dashboard. It's a very, very simple and powerful method. It has an added advantage of being incredibly testable, because you can just issue a curl request to your WebSocket handler with some of this data in, and the WebSocket handler will treat it exactly the same and push that data over the WebSocket to the client. So that was the end of the talk. It was very short. Sorry, I think I skipped through a bit quickly. There's code for Socky and the webhook system called Skyhooks, which up on the server density GitHub account. The talk slides are available on GitHub as well. And all of the illustrations were done by my friend Jonathan Oliver, who is a great illustrator, and if anyone needs any work done, please ask him. If you have any more questions, then we'll have Q&A right now, or just grab me during the conference. Thank you.